Yeah.
It's a great pleasure to have Yusuke Kawamoto with us. We will be starting 7 minutes late, but we have time to make up for it. He will be telling us about quantitative Floer theory and coefficients.
Okay, thanks for the invitation, and sorry for the problem at the beginning. Could you please turn the page? Maybe I'll put a finger up.
Yeah.
Like this. Okay, so homology theory, starts with a choice of coefficient ring, and sorry, could you go? Yeah, sorry. So Floer homology, also requires a choice of a coefficient ring at the beginning, and depending on your choice of coefficient ring, you get different informations. So, for example, some Lagrangians only have non-trivial Floer homology with specific fields like RP2 in CPN or the Chekhanov torus in CPN. And if you want to talk about the Hamiltonian Floer homology, then depending on the choice of coefficients, you get different lower bounds for the Arnold conjecture, for example. Abu Zaid and Bloomberg recently established the Arnold conjecture over field of characteristic P, and Bao and Xu got a lower bound by using Z coefficients, which improved some known bounds prior to their work. So the theme of this talk is to study how much the choice of the coefficient ring to set up Floer homology influences the quantitative information of Floer homology, so mainly spectral invariants. And I'll give a quick review of spectral invariants. So they're important invariants in symplectic topology, and it's defined in the following way. So first of all, you have this isomorphism between the quantum homology and Floer homology, given a Hamiltonian H, and I emphasize the choice of the ring R in the notation. And spectral invariant it's defined for a pair of a Hamiltonian H and a quantum homology class A, and basically it is the minimal action required to represent the class, the Floer cycle corresponding to the class A that we chose. Okay, and once again, I put the choice of I put the ground ring in the notation. I'll put it right next to C to keep track of which ring we're talking about, we're using. And one feature of spectral invariant theory is that it gives rise to a special metric called the spectral metric on the group of Hamiltonian diffeomorphism, denoted by gamma. And the definition goes as follows. So a spectral norm, gamma, for a Hamiltonian H is the sum of two spectral invariants. So one coming from the fundamental class and the Hamiltonian H, and the other coming from the fundamental class and the inverse Hamiltonian. So the Hamiltonian that gives you the opposite flow of H, okay? And then gamma for a Hamiltonian diffeomorphism phi is the smallest gamma for which H produces phi. And by using this phi, you can define a distance between two diffeomorphisms, Hamiltonian diffeomorphisms. And now I'm ready to state the main result. So we focus on CPN today. And on CPN, it was widely known that the value of the spectral norm is bounded by 1. So 1 is the area of CP1 valued with the symplectic form. And this was established by Anton Poldrovich in the beginning of the 2000s. And it was used in some important works on CPN, like the famous work of Ginsberg-Durrell on pseudorotations, and Shelukhin's work on the double conjecture. However, Shelukhin and I discovered the following thing. So we consider CPN, but n has to be larger than 1. And now, even though we knew that the spectral norm gamma defined over a field is always smaller than 1, if we take z coefficients, this value actually diverges. It's no longer bounded. So this is the main result that I want to discuss today. And a small remark for CP2 is that we can also work over z over 14 to get the divergence. It's a pretty maniac result, but today I want to focus on this z case.
Is it true for 14 or is it true for any 14?
Z over 14.
Like specifically 14?
Yeah, specifically 14.
Okay.
Yeah, it's a maniac result. So in the rest of the talk, I want to focus on 3 things. So first, the proof of this theorem A, and I want to show some applications. And I also want to tell you what brings this contrast between the field coefficient case and the z coefficient case. So first, I want to start from showing you some applications of theorem A. So first, the first one concerns a question posed by Nancy Hingston. So Nancy Hingston uses some sort of spectral invariance to study closed geodesics, which is a real number. So she associates a real number to a homology class, a class of a homology of loop space. Okay, and she posed the following question: can it be that the spectral invariant for a class alpha is strictly bigger than a spectral invariant, the spectral invariant for some integer times this class? Okay. And this original question of Nancy Hingston remains widely open. The only progress I think made in this direction is a result due to Chambers and Ljokumovic. It's a pretty recent work which is for F2, and they basically say that this cannot happen if you, under some condition, this is not going to happen. So the condition is written over there. And in this talk, we want to consider the following symplectic version of Nancy Hingston's question. So we pose the following question: can it happen that as the spectral invariant so the symplectic version, symplectic spectral invariance coming from Hamiltonian Floer homology, can it happen that the fundamental class spectral invariant arrive after spectral invariant for integer times the fundamental class spectral invariant? Okay, and from the work of Chambers and Ljokumovic, you might maybe think that the answer would be negative, but Shelukhin and I answered to this question positively. So for CPN, it can happen that this this phenomenon can happen. So namely, for any class, any non-class A, there could be there is an integer k such that k times A spectral invariant arrives earlier than the spectral invariant for A. Okay. Another application is on pseudorotations. So let me remind you that pseudorotations are special Hamiltonian diffeomorphisms that have the minimal expected periodic points from the viewpoint of the Arnold conjecture. So for example, if you consider CPN, the Betti number of the cup length, whichever you take, it's n plus one. So I want you to think of a Hamiltonian diffeomorphism that has n plus one periodic points. Okay, so we call these pseudorotations, and it has been studied, extensively over the past decade. But I think the research was mainly focused on their dynamical behavior rather than the geometry of, the set of pseudorotations or something like that. And so Shelukhin and I thought about, studying the geometry. So what does the set of pseudorotations look like inside the group of Hamiltonian diffeomorphism? Is it a big group, or is it small, or what can we say about it? So basically, we proved that it's like a small group in the following sense. So once again, we consider CPN, and there's a sequence of Hamiltonian diffeomorphisms that escape to infinity from the set of pseudorotations. So it's not a set that is like distributed everywhere, and it's going to stay it's kind of small in this sense. And okay, so I showed two applications of theorem A, but I'll first start with the proof of theorem A, and then I'll tell you how to get the applications and the rest. Okay, so the theorem is about CPN for any dimension apart from one, but I'll just focus on the case of CP2 now. So what's special about CP2 is that we have two special Lagrangians, which is the Chekhanov torus and RP2. And they're special in the following sense. So first of all, they're disjoint. And second of all, they have this property called superheaviness. And but with respect to different coefficients. I'll tell you what that means. So it's a superheaviness is a notion introduced by Entov and Todorovich, and in order to define it, we have to first consider asymptotic spectral invariants of the fundamental class. So zeta R denotes the asymptotic spectrum invariant for the fundamental class with respect to the coefficient R. And we say that, so suppose you have a subset inside CPN. We call this subset super heavy with respect to the unit, but with coefficient R, if we have the following property. So this function zeta R, it has nothing to do with the set S a priori. It just comes from Floer homology, the quantitative Floer homology theory. But if miraculously you can bound this value from above and from below, just by looking at what value H takes on this set S, then we call the set super heavy with respect to the fundamental class. Okay, so we have this. So there's this function that comes from spectrum invariance, and somehow if we manage to bound from above and from below its value by looking at the value H takes on this set S, then we say that it's super heavy. So here's an obvious consequence of super heaviness. So suppose you have a super heavy set S, okay? And you take a Hamiltonian that takes value tau on S. And then, as I said, the value of zeta can be bounded from above and from below by the value H takes on S, which is tau constantly. So we know that this value of zeta R is tau. It's smaller than tau and bigger than tau, so it's tau. Okay, so now we study this kind of weird function mu, which is defined as the sum of zeta for C coefficients and zeta for Z/2 coefficients. Okay. And once again, H is the inverse Hamiltonian. So the reason why we define such a weird looking function is the following. So you pick any r, a real number r, and then consider a Hamiltonian that takes value a on the Chekhanov torus and value 0 on RP2. And let me remind you that this is possible because the Chekhanov torus and RP2 are disjoint. So we can just take such a function. And then from the superheaviness property that I described earlier, we know that zeta for C is A, and zeta for Z over 2 is 0, because the Chekhanov torus is super heavy with respect to C coefficients, and the RP2 is super heavy with respect to Z over 2 coefficients. Okay. So this funny function mu for this special Hamiltonian that we just constructed is computable. It's A plus 0, which is A. And a basic property of spectral invariants tell you that this zeta, the asymptotic spectral invariant, is not bigger than the spectral invariant, the non-asymptotic spectral invariant. Okay, so you can bound it from above by the normal spectral invariant, and then mu is now bounded from above by the sum of two spectral invariants. But here, it's a bit bothering that we have spectral invariants coming from two different coefficient fields. So because the setting is different, it's a bit difficult to deal with this number. So the following is a lemma that helps you with that helps you to deal with the situation. So suppose you have two different rings, R and R prime, and let's say that they're related by a homomorphism J. Okay, and then this map will naturally induce map quantum cohomologies defined for those two rings. And then we want to compare the spectral invariance of a class A, which is in the quantum cohomology of R, and the class that is naturally induced in the R prime coefficients. Okay, and then the lemma tells you that the one that is sent to R prime is smaller than the original one. Okay. The proof is really just diagram chasing. It's just that as I said, spectrum invariant is a value that shows the minimal minimal Floer, the action of the minimal Floer cycle to represent the class. So it's like if you have a class. Wait, do you see the cursor?
No.
The cursor is not visible. So yeah, if you have the, so let's say if you have the cycle for R prime coefficients, so the downstairs, then if you have the cycle on R coefficients, so the upstairs, then you can just naturally inject, and send it to downstairs, and you have a cycle there. So if you're looking for the minimal one, it has to be smaller. There's a chance that you can find something smaller. So that's the principle of this lemma. And in our setting, we had two coefficients Z over 2 and C. And in order to kind of put them together, we want to consider consider Z. Because there's a natural map going to both fields. So, if you want to, for Z over 2, you can just consider the natural projection. And if you want to consider C, you can just consider the natural embedding. And then by using the key lemma, we know that the spectral invariant for C is smaller than the spectral invariant for Z, and same for Z over 2. And the function mu that we were considering, it was bounded from above by the sum of two spectral invariants, one coming from C coefficients, one coming from Z over 2 coefficients. So by using the lemma, we can just bound those two from above by using the spectral invariants for Z coefficients. And then what we get at the end is the spectral norm over Z for H. And now we use a special function that we constructed earlier, which takes A on the Takhanov torus and 0 on RP2, and we've computed its value. It was A by using the superheaviness. And because mu is smaller than gamma over Z, and because A, we have freedom to choose A, it proves that this gamma Z could be, as large as you want. And this also proves that gamma Z is, it could diverge over Hamiltonian diffeomorphisms. So this is the proof for CP. This is a proof of theorem A for CP2. And to consider high-dimensional cases, we have to construct similar, special Lagrangians having similar property, namely the disjointness and the superheaviness. And there were many. So what Shelukhin and I use, after all, is RPN and a Chekhanov type torus inside CPN. But there's so many different ways to construct Chekhanov type torus in CPN, and there's a construction of the Iran cornea, there's a construction to do Pascal Tonkonog, there's a construction to Hang Yuan, and there's just so many. But it was difficult for us to find the Chekhanov torus that has both properties. Like usually the known Chekhanov torus had one of the two properties, but it was difficult to verify that it has two properties. It satisfies both of these properties, and we had to wait until this work of Chanda, Hirschi, and Wang, where they consider this lifted Viana tori. So we appealed to their work. Any questions so far? All right. So now,
actually, I have a question.
Yeah.
So it was key for your proof that this mu of GA is equal to A.
Yeah.
I guess, I guess this inequality in this case, in the previous line, wasn't the case for GA. Is that right? So what was the key there? That it wasn't an inequality, like mu GA wasn't less than or equal to A, but it was actually equal to A. So, I mean, I can go back to previous slides.
Yeah. Yeah, so sorry, I don't know if this is answering your question, but all the inequalities hold for any Hamiltonian H.
Yes, yes.
And we just consider the specific G function GA so that we can compute mu.
Okay, okay.
Is that, yeah, okay. All right, so now I want to tell you how to prove the two applications that I showed earlier. So first off, the first one is what I call the Hingston, symplectic Hingston's question. So what we want to prove is the following. So you look at spectrum variance for Z coefficients, and I want to show that for any non-zero class A, there is an integer K that such that the spectrum variant for Ka is smaller than the spectrum variant for A. Okay. Although the theorem is for any non-zero class, I want to focus on the case of the fundamental class, okay, for simplicity. And so what we want to prove is that the difference the difference between the spectral invariant for fundamental class and the smallest spectral invariant for k times the fundamental class is strictly larger than 0. And I call this notion this spectral depth, denoted by beta spec. Okay. And in order to, the Hingston's theorem B follows from the following inequality. So gamma z is bounded from above by 1 plus the spectral depth for H and the spectral depth for H bar. Okay. And let me remind you that according to the work of Entov-Polterovich, if you consider field coefficients, gamma is smaller than 1. And now I'm saying that over Z, it actually can be bounded from above by 1, but plus some quantities that come from this Z spectrum variance, okay? And in order to prove, so what we want to do is to prove that beta spec, the spectral depth, is strictly positive. And this, but we have theorem A, which tells you that gamma Z could be as large as you want. So in particular, if we have gamma Z larger than 1, then, one of the two betas have to be strictly positive. So that's how, so once we get this inequality, we're actually done, okay? So what I wrote over there is exactly what I just said. We just need to prove the inequality in order to get Hingston's question. So how do we do that? We use the following lemma. So once again, it's about comparing spectral invariants defined over different rings. And here we consider the comparison between Z coefficients and Q coefficients. And our result tells you that actually the spectrum invariant over Q is exactly the same thing as the smallest spectrum invariant defined over Z for K times the fundamental class. Okay. So now there's a chain of equalities and inequalities, which might look complicated, but it's very simple. So the first line, gamma, so we want to estimate gamma Z, and the first line is just a definition. It's just a definition of gamma Z, okay? And the second line, I just insert the spectrum variant of the fundamental class for Q coefficients, so that, it's not doing anything, it just cancels out. I just inserted it. But then the last two spectral invariants over Q for Hamiltonian H and the inverse Hamiltonian is precisely the spectral norm over Q, right? And by using the Z versus Q lemma that I wrote above, you can see that the two terms in the brackets are precisely the spectral depth. You just translate the Q coefficient thing into the smallest, integer spectrum variant. So that's how we get the third line. And then by the result of Entov-Polterovich, the spectrum variant over Q, which is a field, is smaller than 1. So this is how we get the inequality. And then once again, by using theorem A, we get Nancy Hingston's question, but interpreted in a symplectic way. All right, so that was theorem B, and theorem C was about pseudorotations. And the statement that I want to prove is written over there. And I think the reason why it was difficult to study the geometry of pseudorotations up to now was that there was no measurement that separated pseudorotations and the other Hamiltonian diffeomorphisms. So, for example, there's this famous notion called the boundary depth, which might be, which seems like a good measurement to tell you that something is a Hamiltonian diffeomorphism is not a pseudorotation, but unfortunately, the cases where we know that the boundary depth could be large is only for the cases where you know that the manifold, symplectic manifold, doesn't possess any pseudorotations. So there's this kind of technical difficulty there. And our proposal is to use gamma z as a measurement to distinguish pseudorotations and the other Hamiltonian diffeomorphisms. So in fact, for pseudorotation phi, the value of gamma z is, it remains small. It's less than 1, and I spot a mistake in my slide. For any field doesn't mean anything there. It's please ignore that part. Okay, so on the other hand, we know that gamma z can diverge, right, as we've seen in theorem A, but for pseudorotation, it stays small. And also gamma z is just like, gamma in general is smaller than the Hofer metric. So by using these two things, we can use gamma z as a measurement to separate, to tell apart pseudorotations and the rest, and we can prove the statement that we wanted. So this is a proof of theorem C. So in the last couple of minutes, I want to tell you how to get what is behind the contrast between field coefficients and z coefficients. Okay, and the keyword is Poincare duality. Okay, so first of all, the boundedness for fields, it comes from the Poincare duality formula for spectrum invariants, which tells you basically that the spectral invariant for the inverse Hamiltonian H could be recovered by spectral invariants for H. Okay, by looking at this pairing on the quantum cohomology. I'm not gonna define this pairing, but there's this thing that there's this pairing, and for CPN, this formula is super easy to apply. Just for degree reasons, there's not so many, there's only one class that pairs in a non-trivial way. And by using that, you get that the spectrum invariant for the fundamental class for the inverse Hamiltonian is actually minus the spectrum invariant of H for the point class. This is a consequence of this Poincare duality formula. And then by using this, combined with the quantum, the structure of the quantum cohomology of CPN, which is that, so the point class times the hyperplane class goes back to the fundamental class, but with some quantum correction. So by using this and the thing of the triangle inequality, we deduce, we can get that we can prove that gamma k is smaller than 1. So what I want to say is that this this result of Ventov-Poldrovich uses this Poincare duality formula. Okay. But as we've seen, we don't have this bound anymore over Z coefficients. So that means that the Poincare duality formula doesn't work over Z coefficients. Okay. So what's wrong here? What's happening? So actually, the difference between a field coefficient case and the Z coefficient case is that, you know, if you work over a field, there's this no torsion classes. Okay, so actually, in the result, to prove the Poincare duality formula, you use this identification between the filtered Floer cohomology and this Hom of the filtered Floer homology. Okay, and this holds only because over fields you cannot see any torsion classes. Okay, this is the universal coefficient theorem. But now we're working over Z, and in this case, you know, you might have some torsion classes, and this is the reason why you cannot just, you know, use the Poincare duality formula for Z coefficients. The argument doesn't go through. So the question is, how can we describe the spectrum variant of H inverse in terms of, you know, quantitative Floer homology of H? And the result I got with Shelukhin is the following. So we almost have the Poincare duality formula, but you have to consider some error term, which basically measures the persistence of the torsion classes in this filtered Floer homology. So this is a, you know, if you consider Floer homology without any filtration, then it's going to be isomorphic to the quantum cohomology, right? And it has no torsion classes. It's just, you know, it has no torsion classes. But theorem A tells you that when you're, you know, when you're looking at some tau that is when you're increasing tau, at some point you'll see some torsion classes which will eventually disappear. But there's just, you know, extra terms, torsion classes that appear in between, and that's kind of messing up Poincare duality formula. So we have to take this persistence of the torsion classes into consideration. Okay, so I'm actually way ahead of time, but I'm done. So let me summarize my talk. So first of all, at the beginning, we've seen that this value, the spectral norm over field, was known to be bounded. But actually, if you take Z coefficients, it's going to diverge. And this difference is caused by persistence of torsion classes. And this divergence of gamma Z could be used to answer a symplectic version of Nancy Hingston's question. And it has some applications to the geometry of pseudorotations. So that was all I wanted to say, and I miraculously finished very quickly. But thank you for listening.
Okay, well, thank you. Let's thank Yusuke, you know, for his useful talk. However you can. Yeah. So let's see. Okay. So any questions for Yusuke?
So for example, the bound you get on gamma Z, do you know when it's sharp? I guess it's sharp whenever the bound of 1 over C is sharp, or over Q is sharp. But is there any information about the types of H for which it's an equality?
You mean the bound provided by the spectral depth?
Yeah.
When is it sharp? No, actually, I don't know. I don't know. It's an interesting question. I don't know. Yeah, like what kind of dynamical features H have that satisfy that when you have the sharp relationship, how can you characterize a dynamical feature of H? This kind of questions I have no idea. For
Thank you.
yeah, no, I don't know. Sorry.
The 14 looks familiar to me. Can you say where it comes from?
Oh, really? Okay. 14, it comes from the fact that so Chicano torus and RP2, those are the two things that we need. And in order to prove this super heaviness, we have to use Floer homology. And RP2 has non-trivial Floer homology over Z over 2. And the Chicano torus has non-trivial Floer homology over C coefficients. So that's why I was using C and Z over 2. But actually, you can also get non-zero Floer homology for the Chicano torus over Z over 7. Okay. So if you use Z over 7 and Z over 2, and you want to kind of unify it, you can take Z over 14. So that's how, that's why we have Z over 14, but it's maybe your reasoning comes from something somewhere very different.
No, that's a good answer. Thank you.
So you're saying it's
Yeah,
like
it's a technical reason for
Yeah.
for us it's a very technical reason behind it. Not I don't know if there's a geometric way to explain it.
but you're saying it's like Z over N for any N that's 0, 1, 14.
Yeah, exactly. Yeah.
In which context Nancy asked her question? So what was the original problem?
I forgot actually. You were counting numbers of geodesics, I guess.
Mm-hmm.
Yeah, and then she was using basically the fact that if you have different spectral values, then you have different. It should correspond to different geodesics. And then I think she was trying to use this information to get a to see if you can count geodesics in a new way or in a finer way.
Do you have application in this spirit, in this symplectic context?
Yeah, I thought about it. But no, the best we could provide was this pseudo rotation application. So because if you have a positive spectral depth, like this, Nancy Hingston's spirit kind of tells you that there should be more fixed points. So then we started to look into pseudo rotations, but that's the only thing we could do.
So, although this is in a dynamical setting, but if you fix a given Hamiltonian or Hamiltonian diffeomorphism, you can say something like this: that look at CK times unit, right? So then it always lies between CZ and CQ. So if the infimum never achieved, then you have infinitely many orbits for this particular Hamiltonian, which, right, of course, must be degenerate, etc., etc.
Mm-hmm.
So we mentioned it in a remark.
Yeah, right.
Thank you.
Any other questions? Quick questions. So we have more time for discussion. So, but
Can we get notes from the?
Yes, this will be available. The notes will be available on the Zoominar website. Sarah will post it at some point, probably just today or something. Okay, if there are no more questions, let's thank Yusuke one more time.
Thank you.